last Turbo Talk of the day is Johnny Cash doing PPI Geolocation.
Hello, Johnny Cash. I'll keep this brief for a 20-minute talk. Johnny Cash, co-author, Hacking Exposed Wireless, currently on the second edition. Ran a lot of 802.11 cracking utilities, and I'm an aspiring Atari 2600 programmer. So, that is a fun hobby if you're ever looking for a constrained environment. 128 bytes of RAM, you can almost remember all your variables. Senior R&D guy, Crucial Security. I'm also the youngest obsolete guy around. That is roughly me. Me from 5 years ago. Anyway. So for those of you who don't know, 802.11 visualization now looks basically like this. You have a laptop running Kismet probably, you have a wireless card hooked up to an antenna, either an omni or a directional, and a GPS puck on top. Kismet makes 2 files, a PCAP file and a .NET-XML file. It actually makes like 6 more, but that's the only ones we're talking about. And what you do is you take this .NET-XML file, run it through GIS Kismet, which is just the best visualizer currently available until recently, and generate a KML file. And if you happen to be on Windows, it's very similar. You take your Windows box running VisTumbler or something else, export it to any one of these awkward and unmaintained file formats, take it through an unmaintained visualizer if you can get it to run, make a KML file, and look at it in Google Earth. So it really doesn't matter what platform you're on, the basic process looks the same. You got a wireless card, a GPS, and the surveying software does some sort of data aggregation. So it's saying, I saw this network, the most strong signal strength was here. I saw this network, the most strong signal strength was here, and so on. And that's basically what all these different formats are encoding. Take that, run through a visualizer, and look at it in Google Earth. This XKCD comic perfectly summarizes the current state of 802.11 survey formats, which I will give you a moment to appreciate its brilliance. So my goal is to be the 15th competing standard guy, except I want to do it so well that everybody forgets about the previous 14 and it really goes back down to 1, which I'm pretty sure I've accomplished. So the motivation, like I said, the world has too many damn file formats. NS1, NS2, .xml, .gpx, CSV, WTF, I hate them all. Let's clean this up. Why can't all that data be stored in line with the packet? So in this case, we take all this information about the antenna, the GPS, everything we know, run it through the capturing tool, Kismet, whatever, generate a standard PCAP file, which we have all these tools that already know how to parse. Wireshark, Scapy, everybody knows what a PCAP file looks like. Take that through a visualizer and then the KML. So in order to do that, we're going to need to store per packet information, which is called PPI for short. Not pay per install. I did not know this had another acronym until 20 minutes ago. Funny. So the PPI was developed by Case in 2008. It didn't catch on very well until fairly recently, and it allows applications to store per packet information, hence the name, in a standard PCAP file. The cool thing about this is that it doesn't break standard tools. Even if you don't necessarily know how to parse that information, you know enough to skip over it and everything keeps working. So that's the key insight about PPI. So what would this get us if we had this wonderful standard? It would give us the ability to look at a single PCAP file and tell when, where, and what given everything about the state that this packet was captured in. We could then use all of our standard tools to create, modify, and view this data. So Wireshark, Scapy, etc. Stuff we're familiar with. And the most obvious use to me is we could have a universal visualizer. So it doesn't matter at this point what you've captured your data with. Previously, if you capture it with Kismet, you need to use a Kismet-based visualizer. Captured on Windows, some Windows-based visualizers. They're very coupled together. So if everybody stores in this format, they get decoupled. This is really nice if you implement the specification, which I highly encourage everybody to do. It's 100 pages and a lot of fun to read. So, what do we want to store? Let's start with the GPS. That's the most easy. So, if you guys are unfamiliar, how many people have actually used Scapy in here? Anybody? Scapy's great. I love it. So, what you might think here is actually pseudocode, because it looks so easy to read, is actually real code for Scapy. So, if you fire up Scapy, load the contrib modules that implement all of this, and we make a GPS tag. Then we set the latitude and longitude to these, and then we print it out. Fairly straightforward. And then we take this data and we can look at it in Wireshark. And lo and behold, we can see the latitude and longitude. And finally, if you ran this through a visualizer, we get this intersection in New York, which is conveniently located at a 22.5 degree isometric angle you're used to looking at all of your diagrams, which is why I chose it. So, that's a start, but what direction were we traveling? Where was the antenna pointed? What way is the car pointed? We need a vector. Vector details. Vectors specify an arbitrary three-dimensional orientation. They can be relative to each other or relative to Earth. You're all already thinking relative to Earth, because if you think 10 degrees up and 90 degrees to the right, that's relative to Earth. A vector bit mask, a characteristic bit mask, is used to say what this vector represents. So just because there's a vector tag does not mean that is the antenna. This could represent a lot of different things, and you can specify what it represents. So the most obvious ones, like the direction of travel, antenna, the front of the vehicle, and even cooler is if you have something you would like to store an arbitrary dimensional vector on, and I did not think of a bit to assign it, you can have one, or you can assign your own, and there's actually a vendor-specific tag. So if you have some other information you would like to encode in this coordinate system, you can. So V is for vector, make it in Scapy. We say this one is relative to Earth, and it indicates the direction of travel, and it's got a 10-degree pitch and a 22.5-degree heading. Print it out in Scapy, looks pretty. Load it into Wireshark, also looks pretty. Visualize it. Hey, now it looks like we're getting somewhere. Now we have a car and we know the direction it's going. But where is the antenna pointing? We need another vector. Easy to do. Make another vector in Scapy, print it out. This one is 90 degrees relative to the previous one. So if you have if you're an application developer, you actually don't want to keep doing the math. Like I'm going 10 degrees, so this is 100. I'm going 20, so this is 110. You don't have to do that from an application perspective. You can say this is relative to the thing I just showed you. So visualize that one. Now we know which way the car is going and the direction the antenna is pointing. Looks like we're getting somewhere. Okay, that was cool, but what good is knowing the orientation if we don't know what kind of antenna is attached? This is really important if you actually want to visualize this or do some sort of analysis. If I have an omnidirectional on top of my car, it doesn't really matter. I mean, it matters that it's pointed up, but like these vectors don't mean much if you don't know anything about the horizontal beam width. So, A for antenna. I love Scapy. We set the gain. So we set it's 9 dBi gain, 120 degree beam width, which is a relatively wide beam width panel antenna, and you can even encode the model name. Print out in Scapy. Look at that. See a pattern here. Loads in Wireshark, and you can see the gain, beam width, and model name. So at this point, you know everything about the antenna and where the antenna was facing and where the car was. So we're off to a pretty good start. Well, that was cool, but well, how about how fast we were going? Did I say velocity? I'm in acceleration. And temperature? And humidity? Sure, why not? I'm going on a coding binge and I feel like implementing it all. S equals sensor. Set it to velocity, set the value to 20, load it up in the Scapy, prints it out, load it into Wireshark. Look at that. We know that car is going 20 meters a second. If you actually wanted to, you could encode dimensional information as well. So if you actually had a 3-dimensional accelerometer, you could encode that there. That gets a little more complicated for a 20-minute talk, though. So that was cool, but I was told there would be pretty pictures. This whole talk was supposed to be about some universal wireless visualizers. So where are they? Here we go. So this is the testing area, aka my neighborhood. You'll become very familiar with it over the next 5 minutes. So first thing we do, we fire up Kismet. This is normal, unpatched Kismet. We hook up a GPS, drive around my neighborhood. We take that data, run it through GIS Kismet, which is the standard, out there already visualizer for Kismet. Run through it, make a KML file with it, open it up, and this is what you get. Highlights include Gay Bump Monkey, which seems to come and go, and a few other networks. I think they only put that there because I knew I was collecting test data that day, because I really haven't seen it. Just once. So this is my neighborhood from like the current to today's stuff that you can go download. I narrowed it down to 3 networks to show you, to give us a smaller set of data and make it easier to illustrate what's going on. And just to be perfectly clear, what's happening in this visualization is Kismet is generating this kismet.net text or netxml file, and it says, here's the peak position. The visualizer then, drops this target on it, and that's all the analysis that's going on, Basically, strongest packet, drop the thing there, which is a good start, but let's see what we can do to improve it. So here we take the same data, generate from the same Kismet survey, and we run it through my PPI universal visualizer. edit the config file. I want to tell it in this case that it is scaling it to 100 meters, and to use linear scaling, and which is right down here. So we run through my universal visualizer. So this is the same PCAP file Kismet created earlier. And we go straight to a KML file. It goes, pre-processes, processes all the networks, gives us this KML. So what does this look like? So this is what we had before. No PPI information. And this is what we get when we know the signal strength and location of every packet. Stronger, brighter lines indicate stronger signal strength, and shorter, darker ones are less signal strength. So this is a kind of noisy one. I did a few more examples. This is another network that we saw earlier, HP setup. This one is a little prettier. Watch the lines fade in. So stronger, brighter lines, stronger signal strength. I mean, even at this point, we've gained a lot of information. For example, this network is basically brighter or stronger. We can see it from farther away. That was not in any way conveyed with the previous aggregated data. You could say, well, the strongest packet was here, but you couldn't really say how far away did I see it. That information was just lost. And finally, here's last third example network, Skoroko. I'm not sure how you say it. They're my neighbors. I should probably know their name. Anyway, this one is actually almost like a casebook illustration. It looks really pretty. The closer we get to this house, the stronger lines, the brighter lines, they get up until this point, which was the peak packet, which we can see because that's where GIS Kismet dropped its target, and it starts to fade away. So, I mean, that's a pretty good start, right? We haven't added any more complexity, and we're getting this out of, the tools that are currently available. But I've been working on this for well over a year, sadly, and all you have are some bar graphs and Google Earth. Oh, no. Say hello to my little friend, Wi-Fi cannon. +5 charisma, +8 gain, 30-degree horizontal beam width. Certainly adds a level of badassitude to the whole thing. Combine that with my cherished 2008 Cobalt SS with a 260 horsepower supercharged Ecotech engine, a ridiculous wing for +5 horsepower, and an optional sunroof, which will be key, we'll see in a moment. Add that to a directed perception servo, which has 360-degree pan, plus or minus 30 degrees of tilt, and is 100% software controlled. Stick that on top, drop in Wi-Fi cannon, as mentioned, a DVI antenna with 30-degree beam width, and the completely useless lights. And we have Servobot, time to roll out. So this is me in my neighborhood, trying definitely not to attract the local PD's attention. And the servo spins around, as you can see in this awesome time-lapse picture, and as it spins, it knows its relative rotation, and it's writing out the PCAP in that file format I just gave you and spent 18 months developing. So, I took Servobot out, scanned in these 4 positions, and then after that, I did that, I was like, I should get some more distance on this, so you do 5, 6, and 7. So each one of these represents where I parked my car, poked that thing out, stood there for like 60 seconds, and was hoping nobody paid too much attention. So I did that 7 times. So here's what we get from that. So here's the first network we saw earlier, offline, GIS's Kismet's guesstimate as to where it was. Then I park my car here. Servobot starts scanning. It's the same color scheme as before, so darker, shorter, not good, brighter, longer, better. And it starts to rotate, and we get this data. So it seems like it's generally pointing in this direction. And we didn't get a whole lot of packets, but it's pointing this way. At this point, you can immediately rule out this house, and this house, because it would be pointing right at them if it was either of those. Go to another location. Servobot starts up. And you can see this gap here is pretty interesting. It's definitely not that house, and it's also sort of pointing out across the water, so there's nothing to see. Servobot keeps spinning, and at the end of the day, you get a picture that looks like this. So it's sort of pointing this way, but it's not the easiest to read. Servobot comes over here, starts spinning. This is pretty interesting. It's pointing this way, and finishes out. So you have to sit here and squint, and I don't have the time because it's a really short talk. But if you sort of like to say, well, it's definitely not this one because it would be here, and it would probably have more signal strength on this one, and it's definitely not this one because this one would be pointing way over there. I guesstimate it, and I put it in this house after having stared at it for a while. It's intuition. That was not mathematically derived. There's no solver in here. It didn't do any trigonometry. It's just looking at those lines. So I go across the lake to get a scan, and we get these two packets. And this is pretty interesting because this is what wireless engineers call multipath, which is the word anybody in wireless uses to cover their ass when they don't know how to explain anything. It's just multipath. That's how MIMO works. That's how you get great cell phone coverage in cities with this whatever. It's the great CYA. Nobody knows. Nobody can explain it. Here, I can illustrate it. This is a rare event. You won't see this from many other wireless guys. Multipath. You can see it. So, to put this in perspective, these two packets, there's two of them right here, bounced off this guy's house. I can tell you exactly which two packets. Which two packets? Open up the PCAP file, filter on the network, and then filter on the position, and we are left with two packets. Look at that. Those two packets bounced off his house. Yeah, it's awesome. You should be applauding. That's packet one. That's packet two. How cool is that? So this is an overlay. If you look at all the information we've gathered, the vertical stuff came from Kismet, and this was captured by the servo. So I have, like I said, you stare at this long enough and you think it's probably here. This is a similar network, and GIS Kismet couldn't differentiate between these. It doesn't have that much information. They're basically on top of each other from Kismet's perspective. So here we do a first survey, and it's definitely pointing this way. Do another survey, and the intensity of these lines tell me we are much, much closer to this. The signal strength has gone up dramatically. So we're basically on top of this. It's like white hot. And the color scheme here is representative of physics, in case you're curious. Everybody seems to think I'm doing it wrong, but white is hotter. So this is like white hot here, and we do this from over here, and it's less, it cools off. And do another survey, looks like that. This one is actually strong enough or bright enough that you can see it from across the lake. This is pointing this way. This one is actually pretty easy to read. I'm pretty confident saying that one lives there. And then finally, here's a third example real fast. Did a quick survey with the servo. 1, 2, 3. So at this point, you get an impression it's down this street somewhere. And then we do one from here. And, there's not enough angle resolution to say if it's this one, or this one yet. And these last ones I did to fill it out. So the farther you get away, less packets, less color. 5, scan 6, scan 7. So this is interesting because you can actually see this one from way over here. Finally, I got so frustrated looking at that, I did one more scan from right outside their house to figure out which one it was. And I think it's here. So that's where I put it. So I'm going to jump out of PowerPoint and give you guys an awesome live demo of my command line visualizer. So I'm on my Linux VM right here. This is the INI file you can configure. I set the distance scaling to exponential. You can do linear or you can do static. And when you're scaling these things, you can either scale them across the signal range for a given network or from a signal, the entire range you saw in the packet. So it depends what you're trying to compare. Do we care how strong the signal is relative to everybody else in the neighborhood or just the network we're looking at? And you can visualize them both and you get interesting results either way. And you should play with it. So this one is per BSSID on both dimensions. Fire up the visualizer, verify the settings. Right now it's computing the spread across the dB, which is important. You have to think this is actually going across like 10 orders of magnitude when you do the math across that range. Computes the dB spread, and then it starts generating a KML file. So go over here, copy it over to my Windows box. VMware does not feel particularly speedy today. And we get this new file on my desktop. So this is the generated from that street. So this was generated, right now, real time. That was real demo. So I took this survey at an intersection, which is fun to do because I'm at a stoplight with a servo in the air, hoping I get everything just right. So you can look through here, and these are similar graphs. They're just in a different setting. That one's over there. That one's over there. This one's over here, et cetera, et cetera. The cool thing about this is we can grab Google Street View guy over here. And there you go. It looks like it's that way. I mean, I'm no expert. Well, maybe I am. And you can poke around and see some other ones too. So that was pretty cool. That's a nice feature. I don't think I've seen a visualizer do that yet. So that was cool, but nothing. It was cool. Okay, where is all this code? Wireshark merged, Scapy merged, and Kismet merged. So you don't have to go download any of that stuff. It's already in there. I basically built this into the world and didn't tell anybody until it was done. You can get the SDK from Harris, assuming the Harris IT monkeys have done their job and uploaded it. I think I need to give them some bananas or something. There's a link. The SDK includes a C++ library for reading and writing all of those tags I was showing you, a Python state machine, which the visualizer is built on top of to show you how to interpret them, so there's no ambiguity. I hate standards who have ambiguity. You should have to implement it before you give it to anybody. And then there's the two visualizers that I was generating all this data with. So you should be able to download it there. I will not be surprised if they haven't put it there yet, though. So supporting vendors: Harris, Praxis, SRT, Wireshark, Python, Scapy, and Kismet. So yeah, that's a pretty good list. That's like basically the entire industry. I think it's fair to call this an industry standard at this point. And to quote the venerable John Hodgman, you're welcome. So if I have any time left, feel free to ask me questions. Thanks to Charlie, Jody, Tyler, et cetera, et cetera. Nick, kind of a big deal, Petrillo, who I don't think showed up. Thanks, Nick. And everybody else. So if there's any questions, I don't think I could be bumping anybody's time. So feel free. Yeah?
Did you try anything with clients, positioning of wireless clients?
So that's an interesting question, is have I tried to do any location with clients? And so if you run, right now the visualizer, as you could download it, just filters out on beacons because they come out at a fixed rate, at a fixed, every 1/10 of a second usually, and at a fixed rate. So when you're trying to locate a client, it gets significantly more complicated because A, it's bursty traffic, and B, the rate varies, which would actually vary the signal strength thing you're trying to do. So you could definitely tag client-based packets with this, like that's already being done by Kismet when you write out the data, but in terms of visualizing it, you would need to try to, it's much less easy to read. You need to do something to work around that. So, but you could definitely tag any packet with it, so it's already sort of built in. It just doesn't look as pretty. Anybody else? Okay, well, thanks for coming. That is 18 months of my life and 40 hours worth of work on my slides for a 20-minute talk. So there you go.